Okay, hi guys, so we'll be seeing more on enthalpy. So we can write that dq is equals to c dt. So at constant pressure we can write that dqp is equals to cp dt. So we can write that dqp is cp dt. So dqp is equals to dh, which should be equals to cp dt. Okay, so if change in temperature is 0 or dt is equals to 0, then we can write cp would be infinite or will tend to infinity, as we can write that cp would be equals to dqp upon dt, which should be equals to dh upon dt. Okay, so we can write if dt tends to 0, then cp tends to infinity. So molar enthalpy change can be written as dhm would be equals to cpm dt. Okay, so similarly for n moles of a substance which can be solid, liquid or gas at constant pressure, we can write for n moles of substance which can be solid, liquid or gas at constant pressure, we can write that dh would be equals to n cpm dt. Okay, so let's see rather case 1, where we have if cpm of substance is temperature independent, if cpm of a substance is temperature independent, then we can see from T1 to T2 we can write dH as equals to n cpm dt. So we can have delta H would be equals to n cpm delta T. Again we can have the limits from T1 to T2. Okay, for now I'm erasing this T1 to T2, but I hope you get the point. Next, if cpm of substance is temperature dependent from T1 to T2, then what we can say is would have case 2 in which if cpm of a substance is temperature dependent, then we can have cpm as a function of temperature. So we can write let's suppose a plus bt plus ct square. So in the equation, which is delta h or dh is equals to n cpm, so in place of cpm we have to substitute these values, so we'll get dh equals to n a plus bt plus ct square dt. Now when we integrate it from t1 to t2, we can get something like delta h would be equals to n, or rather let me write it in next line itself. So we'll get delta h equals to n a t2 minus t1 plus b by 2 t2 square minus t1 square plus c by 3 t1 cube or t2 cube minus t1 cube. Okay, So for solid liquids we can write that Cm would be equals to Cpm, which would be equals to Cvm. Okay, and for solids and liquids, the condition that Cpm minus Cvm is equals to R does not hold true. Okay, so for solids and liquids we cannot have this equation in place. Okay, but for an ideal gas we can definitely say that Cpm minus Cvm is equals to R, and from here we can actually say that Cvm would be equals to Cpm minus R, and if Cpm is temperature dependent, as in we saw in previous example or previous case too, so if this is temperature dependent, then obviously Cvm would also be temperature dependent, which can be written as A plus Bt plus Ct square. This is Cpm minus R. So we can get Cvm as A minus R plus Bt plus Ct square. Okay. Now let's consider a case wherein H is equals to, or rather enthalpy is a function of temperature and pressure. So if enthalpy is a function of temperature and pressure, we have seen the derivation in which we can write dH as del H upon del T at constant pressure times dt plus del H upon del P at constant temperature times dP. Okay, so we can write dH in the form of this differential from the derivation we have seen few lectures back. So we'll be continuing seeing on this further from the next lecture onwards. So till then, good luck and goodbye.